forgot to ask you, only last night when I prepared my class.
So it's F-O-U.
F-O.
Field O is the valuation.
And the maximal ideal uniformizer?
I didn't uniformizer pi, and I didn't use any notation for the maximal ideal.
So that's more, not so far from what Okay, so we are still talking about building. This is a subject which is worth studying the kind of independently of the rest of the course. The way I'm going to present it is really by concentrating on the example of the buildings of GLN or SLN or PGLN. It's basically the same building. There is a rich theory of building associated with every simple group. I will say a few words about that, but I think it's kind of better to get to know one example. Unfortunately, there is almost no discussion in the literature concretely on this example. Somehow, the literature usually talks about the general case, and one doesn't see the particular case. So I think it's, and especially for the combinatorial application, this will be enough for us, and it's kind of more concrete, less abstract. So let F be a local field. So, for example, F can be the periodic number, so I understand that we have talked about it, or the Lorentz power series over a finite field of order Q. Basically, that's almost the general case, because the most general case of local non-Archimedean field is it's either a finite extension of QP or one of these. So basically, these are all the examples which we care about. O is the ring of integers in F. So in the examples, this is ZP, the periodic integers, or the polynomial, or the power series. This is the Lorentz power series, this is the power series. M will be the maximal ideal. D maximal in a local, in this situation, there is a unique maximal ideal of O. This is now O is exactly in the language of valuation. O is all X in F. You talked about valuation or about absolute value?
I used valuation.
So that the valuation of X is greater or equal 0, and the maximal ideal is all X in O, such that the valuation of X is strictly more than 0. This unique maximal ideal, and this ideal is this is a principal ideal domain, so it's generated by one element. And now there is a choice in this element. The element pi is not unique, but usually we kind of fix it, and it's called, for some reason, uniformizer. I don't know, it's not such a good name, but that's the way. Uniformizer. So in the examples, pi will be either P for ZP, the element P, we think of it as the prime P, or pi equal X in the case of power series. Now let V be the vector space F to the D. You use D or you use N?
I used the D.
What?
D.
D, okay. F the D, and then let N be a finitely generated O submodule of V. So you see, V is a module. V is a vector space over F, and therefore is also a module over O. But as a module over O is not finitely generated, we take a finitely generated O submodule which generate which span to generate V over F. If we think about it over F, so it contains a basis. And I don't know if you prove it or you leave it as an exercise. So if you didn't prove it, I will leave it as an exercise. That such a module, that there exists a basis alpha 1 up to alpha d of V over F, such that L is exactly the O module spanned by this basis. So there is a basis which is a basis over the field for the vector space. And L is the O module generated by this. You define it right away like that?
I gave this definition and then I mentioned it as an exercise.
That this is equal, okay, fine. Now, we say that L1 is equivalent to L2 if there exists some T in F which is non-zero, such that TL1 is equal to L2, and this is an equivalent relation that's easy to see. You can go back and it's transitive, and these are the equivalent classes. And we are ready to define the building or the simplicial. Just a moment, maybe a remark that we will use. Every T in F, which is not zero, is equal, can be written uniquely as T equal pi to the n lambda, say, where n is a number, is an integers, and lambda is a in O star. By the way, O star is, by definition, this is all x in O, such that x is invertible in O, and this is exactly equal, I don't know if you mentioned this, this is exactly equal to O minus m, which means this is all x in O, so that the valuation of x is exactly zero.
We proved it.
What?
We proved it.
Okay, good. So what happened is that we take the valuation and we multiply it by basically this n is the minus the valuation, right? N is minus the valuation of t. Because if the valuation of t is something, we multiply it by pi to the minus the valuation. Sorry, n is the valuation. So we multiply it by n to the minus the valuation, and then we get an element of valuation 0, which means we are getting an element which is invertible in O. Okay, I mean, just think about it. If you think about the power series, right? You have a power series, then the valuation is the starting point of the Lorentz power series, and then you multiply it by an appropriate power of x in order to have it inside O, first of all, and you want that the constant term will be non-zero. Okay, you all with me? I mean, I don't want to lose you about this trivial point. I'm not sure how much you are experienced with working with local field, but that's basically his effect. Okay? Is it clear? I mean, don't be shy. Okay. So now, it means, by the way, that if L1 is equivalent to L2, and that's something very important to remember, then really there exists n in Z such that L1 is pi to the n times L2, because in principle I have to multiply by any invertible element of F. Any element in F, non-zero element in F. But such an element is pi to the n times lambda. And if I multiply a lattice by lambda, because lambda is an invertible element of O, then lambda L is always equal to L. Because lambda O, what is L? L is something of this form. If we multiply something of this form by an invertible element of O, then we are getting the same thing, right? Because lambda times O is equal O. Is it clear? So, which means that basically what we do to lattices, we kind of shrink them, or how you say, what's the opposite of shrink? Or
Stretch.
what?
Stretch.
Stretch we talk, like either we shrink them or we shrink them, right? And that's the only thing we kind of can take them up and down along the levels. That's what we are doing to a lattice in the same equivalent class. Okay, and now let's define B D of F. It will be the simplicial complex. In order to define a simplicial complex on the set of vertices we usually write, we will write B0, we will forget the D and F. B0 will be the equivalent classes of these lattices, and the set L0, the equivalent class of L0 up to Li, form an I cell if there exists representative Li prime in Li in the class such that so this is always when I define it up to an order, so I can always arrange if in some order this is possible, then this will be a set such that L0 is inside L1, prime is inside Li prime, but it contains time Li prime. So L0 is inside L1, is inside Li prime. This is something similar to what we remember from the spherical building associated with finite fields. And in a minute we'll see that there is a connection. But here it's somewhat different. We are really talking about O modules, and we want that if we take the top one multiplied by pi, it's inside this one. Okay? Right here, the part of the assumption will be the notation that O over M is always a finite field. So let's say that it's Q, it's FQ. Okay, if it's the periodic number, this is FP, but I will use always the letter Q for the what sometimes is called the residue field, the finite field, which is O over M. Now note, and that will come many times, so I want you to pay attention to that for every L, it doesn't matter what is the lattice L over pi L, you see, and L can be this Li, this is always a finite index. This is like taking the lattice and kind of pushing it by pi, so this, because pi is inside O, then this is inside, pi of L is inside, and this is isomorphic to FQ to the D, because L is basically O plus O plus O plus O D times. Right? That's what we know from here. So L over pi L is simply the finite, it's the finite vector space, right? Because this is the same, right? L is sigma O alpha I, pi O is exactly M, so pi L is sigma M times alpha I. So if we divide this by this, we are getting D copies of O mod N. So it is isomorphic to a vector space. So right away from here we see, therefore, the dimension of BDF. Okay, let's now be careful. What is the dimension of BDF? This is I cell. Now, in order to have a sequence like that, 0 up to Li, what is the maximum possible I? We know that we are talking about a sequence here of submodules inside Li prime, containing pi Li prime, right? So, by what is called the homomorphism theorem, right? Every submodule, a sequence of submodules like that, when you pull it down to FQ to the D, we are getting subspaces of FQ to the D, right? So this is a sequence of subspaces of FQ to the D. What's the length of this? The length is between 0 up to at most D, right? So the dimension is at most 0 up to D, which means at 0, no, okay, let's be careful. It's really 0 up to D minus 1, because if this is the top one, right? Now they are not equivalent, Li prime and Li. So this one, so all this together is a vector space of dimension D. So if we have here a truly increasing sequence of subspaces, so the total length is D plus 1 from here up to here. 0, 1, 2, etc. up to D. So the total length is D plus 1. But this one is not counted because this lattice is equivalent to this lattice by definition, right? This lattice is equal to this lattice times pi. So the total length is at most D. So I is at most D. No, I'm confused.
Yes.
L0 is 1. The dimension should be D minus 1. So
the cell is of size.
yeah. Sorry. This is D. Yeah, this is D. And this is like 0, 1, 2, up to D. Okay, yeah. So this is like dimension 1. So the series is, this is from 1 up to D. So the length of the series is at most D, which means that as an I cell, this is at most D minus 1. Let me, it's a simple point, but I got confused, so better I'll repeat it, okay?
Just want to say that last time I defined the cells as cliques. So, I don't know, it's an exercise to prove that this definition is a clique.
You define it as, you define only what does it mean to be a neighbor?
I define just what is it mean to be a neighbor, so the edges, and then I define the cliques, but it's the same thing, I just want to comment. It's the same definition, and it's not so hard to see it, and this is much more beneficial and much more useful definition.
What?
This definition.
Yeah, this gives you the full structure. We'll see that this is equivalent. Okay, that will be a good exercise, but just a second. So here I define you what is exactly, and from the other definition you don't see right away what's the dimension, right? But
Yeah.
here you see right away what is the dimension. So let's continue with this definition, and then I will give the other definition. So again, we want to take sequences of modules, right? such that you remember that in order to be an I cell contains I plus 1 point. Now I'm taking a sequence of modules between L and pi L, and so I have this L, and I have another one, another one, another one, another one, another one, another one, another one. I cannot take pi L because pi L is equivalent to L. I can take either this one or that one, not both of them. So so the length of the sequence will be at most D, right? Because this is a vector space of dimension D. Right? Now it's clear. The length of a sequence of modules like that is going to be at most D, because when I pull it down to L mod pi L, I'm getting a sequence between pi L to L. But I'm not counting this one and this one give me the same point. Right? They're equivalent. So I'm taking only those in the middle. So in the quotient, which is a vector space Fq to the D, I can take either the full space or 0, but not both. Okay? Remember that in the spherical building, we took neither 0 nor the full space. We didn't allow to take them. If you remember, we took only proper subspaces. Not here we do allow to take them, but only one of the two. So the total length is D, is at most D, which means that the dimension of the cell is at most D minus 1. In fact, it is, in fact, the dimension of BDF is equal to D minus 1, since we can start with some L. You know, you have L and pi L. If you have, in fact, I'm going to prove you that at the same time that this is a pure, what we call the pure simplicial complex, namely every cell is contained in a D minus 1 dimensional cell. All maximal cells are going to be of dimension D minus 1. Why? We saw that it's at most D minus 1. But now I claim that if I start with any cell, I can embed it into a cell of dimension D minus 1. Why? If I have such a cell with Li, you know, so I have some sequence between L to pi L. I can make it a final sequence by adding subspaces here in F Q to the D to make the sequence to be of length D, which means dimension D minus 1, length D. And then I can pull them back to submodules between L to pi L by the homomorphism theorem. No, the homomorphism theorem basically tells us here that there is a one-to-one correspondence between subspaces of Fq to the D and submodules of L containing pi of L. Is it clear, or I should write it down? Some of you don't answer me today, and I don't see in your eyes if it's okay or not, so please. It's okay. Okay. So if I have here a sequence of one, I don't want to waste your time by doing trivial things. On the other hand, if you don't digest this, then this is going to play a very important role, and it takes time a little bit to digest somehow this simple fact, but now I have to get used to them. So what happened is that every space here, can be pulled back. Every sequence here can be pulled up to give you, and in fact, and then I would say start with such a sequence and make it final to get a sequence of length d minus of length d, i.e. d minus 1 7. So the corollary is that BD of f is a pure simplicial complex of dimension exactly d minus 1 and every. You remember that the spherical one, when we work with dimension d, was something of dimension d minus 2. Right? Here is d minus 1, is one more. Okay. I want now, it's going to play an important role, so I want to define type function, or if you want, coloring of the vertices of this simplicial complex. So this is going to be a building, we'll call it, but building is not yet a name we're really using, but I will call it the building, I will call it the building of f of dimension d or whatever. So if I say building, I mean this one. I want now to type function or a coloring function. I want to give, we're going to define a function tau on the vertices, yeah, I promise, sorry. I want to make the connection between this definition and what Ria gave you last time. The basic thing about simplicial complex is, first of all, to tell you what is the one skeleton. The one skeleton means what is the graph. We know what are the vertices, all these equivalent classes of edges, and the question, when we have an edge, when they are neighbors. So according to my definition, so L1 is a neighbor, there is an edge between L1 and L2, if and only if there exists L1 prime in L1, L2 prime in L2, such that L1 is inside, prime is inside L2 prime, and this one is inside pi L2 prime. Well, you may ask why this is clear that this is if and only if, because in my definition maybe I can switch the order, but this is a, if we just think about it between two, this is clearly a symmetric relation. Why? Think about it. If I will write here pi of L1 prime, I don't have to say, but pi of L1 prime is clearly inside pi of L2 prime, because L1 prime is inside L2 prime. So if I multiply this by pi and I shrink it inside L1 prime, then in Hebrew we say kal vachomer, so I don't know how to say it in English, but then certainly if I multiply L1 prime by pi, it will be inside pi L2 prime, right? So you see that either this way or this way, we are getting that they are neighbors. So we can define, first of all, just the graph. We can define when two edges, when two vertices are neighbors, and that will be the same definition, as this is a special case of my definition. And then, the way we are defined the building is said, an I cell is a clique, namely, an I cell, so now this will be an exercise. So let's see first, or maybe remark. Clearly, if L0 up to Li is an I cell, then clearly each Li is a neighbor with Lj. It's adjacent to Lj by definition. If you want, I mean, a simplicial complex if you want, because it's a simplicial complex, namely a simplicial complex contain, if a subset is in the complex, then every subset of that subset is also in the complex. So you can say, if this is a simplicial complex, then of course, but you can also see it from the definition, because if L1 prime is inside L2 prime, and this one is containing pi of Li prime, then it certainly contains pi of L2 prime, etc. So you see that they are really neighbors. The claim is, and this is less trivial exercise than the other direction, that if we have, if L0 up to Li is a set such that Li is a neighbor of Lj for every, not Li, Lt is a neighbor of Ls for every t different than s between 0 and I. So if I have a set of I plus 1 equivalent classes, which means I have a set of I plus 1 vertices in my building, in my simplicial complex, that they are all neighbors, then L0 up to Li is an I cell, which means that this is called a clique. A clique means it's a complete graph. If L0 up to Li form a set of I plus vertices, that every two of them are connected by an edge. So this is like the complete graph on the I plus 1 vertices. This is called a clique. If you have a clique, then this is necessarily an I set. And vice versa. Of course, vice versa is the other direction, which is clique. This is not completely trivial. I mean, it's a good kind of a linear algebra exercise. Maybe someone wants to do it as homework and send me a proof. Maybe we'll give you an opportunity next time to present it. It requires some linear algebra thinking for it. It's not very difficult, but it needs something. Okay, I don't want to stop now. For that, now I want to define the coloring, the type function. So this will be, I'm going to give a coloring to the vertices, and that's going to be a number between 0 to d. So I prefer to think about it as an element of the group Z mod dz, and I will do it in the following way. Several ways to do it. I'll do it in the following way. We want to define such a function. So this function, we'll think of it as giving colors to the vertices of the buildings, and the colors are going to be numbers between 0 to d minus 1. And we'll do it in the following way. Let, first of all, L0 be the standard lattice, O of E1 plus O of ED, when E1 to ED is the standard basis. Now, I claim that, and this is clear, there exists, given L, there exists a unique N in Z such that pi to the N L is inside L0 with minimal index. let me explain. In L0. Let's explain. I know that I can always push L to be inside the integers. This is clear because I start, you see, if L is O alpha 1 plus O alpha D, all right, I can multiply L by some I power of pi, Actually, I don't need even the minimal in the first, for the first definition. Let's say there is. So let me start. There is, later on I'll say, not minimal. Let's start with this. For the definition of pi, I don't need to have a minimal. I will say in a minute about the minimal. But there exists n such that it's inside L0. First of all, there exists, that's clear. I can multiply if I'm already inside, fine. If I'm not inside, then just multiply by I power of pi, and then I'm getting integers, right? If you take any p-adic number, you can multiply it by p to the something, and then it will be integer. If you take any Laurent power series, if you multiply it by an I power of x, it will be inside the integers. And then let's define tau of the equivalent class of L to be log to the basis q of the index of L0 in this pi to the n L mod D. Namely, I think about it as an element in Z mod dz. I claim, first of all, that this is well defined. Claim 1, tau is well defined. What I mean well defined? Namely, what happened here? I took some lattice L, I multiplied by some I power of pi, and then I'm taking the index in L0. So I made two choices here. First of all, I took I power of pi. I didn't tell you which I power. I just told you take any I power that you put it inside L. Maybe if I will take one power and you will take another power, maybe we'll get a different number. I claim no, why not? Because if you will take some power, and I will take another one, which is much larger, then my pi to the NL will be much deeper, right? But what will be the index? Each time we multiply by pi, we are getting, what is the index? Q to the D. You remember, if we take a lattice and we multiply it by pi, the quotient is FQ to the D. So the difference between two different choices of n's is always by multiplication. The index is shifted by q to the d. If I take log of it, I'm getting extra d. Log to the basis q of the index is another d. If I take it more d, then it doesn't matter. So you see that the n, it doesn't matter. What is the n? Okay? But now I claim that it also doesn't matter what is L. If I take another element in the same equivalent class, this is the second problem in this definition. That I took it as a definition for an equivalent class. Right? If I take now another representative from the same equivalent class, so what's the difference between them? Again, one of them is pi to the something times the first one, right? So, and then I'll push both of them by some big pi, to put them into the integers. And it doesn't matter. I know that the fact that one of them was pushed by another pi it makes no difference. I already mentioned that. I mean, the difference is only by factors of the differences in the indexes are by factor of q to the d. If I take log, it means that by addition of d, which means that mod d, it's well defined. Is it clear? I don't think I have to write it down, right? So that tau is well defined. By the way, if you want a nice exercise, let me give you an exercise, another nice exercise. If L is equal to O alpha 1 plus O alpha d, right? I basically defined tau for a lattice, and I really showed you that it's independent of the equivalent class, that it's well defined on independent class. So how to compute? If you really want to compute it, the color of a lattice, then look at the matrix M, which is alpha 1, alpha 2, alpha d. You can put them in rows or in columns, whatever you want. Just you take this as matrix. So this is D by D matrix, right? Take the determinant of M, and tau of L is equal to the valuation of the determinant of M taken mod B.
So I actually gave that definition.
What?
I gave both definitions last time.
Oh, you did last time. Oh, so you don't. I see. Okay. You gave both definitions?
Both definitions.
Okay, good. Sorry. Okay, sorry. And you show that they're equivalent?
No.
No. Okay,
It's
so
a
that's
good
okay.
exercise.
But that's basically, think about it, what happens here. But that's kind of, it's good to, let's give you an intuition. You know from linear algebra that the determinant is essentially the volume of the matrix. Right? And what is the volume of the matrix here? Really, you see, if you take you can normalize that the volume of the standard lattice is 1. And the index is, in the index kind of express for you the volume, well, to be honest, is like 1 over the volume in this case. Right? But somehow you're not surprised that you can really detect from the determinant what is the index inside the full, because this really expresses the volume of the lattice. What is more important for me, because that's kind of an effective something that I don't think you show here, because that's something which we'll need even today, and I want to show the following. I want to say that there exists, given L, there exists a unique n in Z such that pi to the n times L is inside L0 of minimal index. Now, I don't want just to understand I don't want just to understand that you are on finite index, but I want really to look what is the minimal index. I want to put you to the integers, but on the nose, namely just to the minimal possible index. If you're outside, then I have to multiply the lattice by some power of pi. If you are already inside, maybe you're deep down inside, then we'll multiply it by also by power of pi, by a negative power of pi. Right? If we are very, very integers, like all the alpha i's are divisible by powers of p, we can divide by p. Namely, we can multiply by p to the minus 1 to bring you up. So if you are inside, I bring you up that you come to a minimal index. The only thing, so this is always we can bring you to a minimal index. That's not a problem. Why this is unique? Because think about it. If you would have two representative, if there are two such pi, if you have two representatives which are both integers and both of the same index, and they are equivalent to each other, it means that one is obtained from the other by some multiplication by pi, or by some power of pi. And so the index of this, and I can assume that one is obtained from the other by multiplication by a positive power of pi, which means that the index of the next one will be the index of the first one times something, right? If I multiply by a positive power of pi, then I shrink it down a bit more, so it's not minimal anymore. So the minimal one is unique. I can have two lattices of the same index, but if two lattices of the same index are equivalent to each other, both integers and are equivalent to each other, then they must be equal. Okay? Is it clear? That's going to play a role in what we will do after the break. So I hope this is clear enough. Okay, let's take a break now, and then we'll